In this video, I want to talk a little bit more about why we twisted to get the sine and cosine. There's a kind of a simple reason why q equals 1 behaves better, at least in this perspective, than any other value of q for the generalized Lucas sequences, and that's symmetry. Okay, so sine, one of the most important things, one of the most beautiful things about sine and cosine are that they are, odd and even functions respectively. I think I switched something and forgot to switch that. Those are odd and even respectively. And so un and vn, those were just sine and cosine, admittedly of complex arguments, but they're still odd and even. They had corresponding symmetry. But one of the annoying things, although one of the hints of why we had to twist again, was that fn and ln had these minus 1 to the ends in them. They have a less simple and beautiful symmetry. So now what we did, of course, as explained in the last video, is we really created a different kind of Lucas sequence with a different recursion rule, where it's iun minus 1. That says that q equals plus 1, because the minus sign is automatic. And that allowed us to identify it with sine and cosine. And in fact, one of the simplest reasons is that that's necessary for us to have to be able to have even odd symmetry, period, much less sine and cosine. Those are these very special functions. So let's look at that. So just some nice, it's much more low tech than some of the stuff we've been doing. And then I'll bring it back to the matrix case at the end of this video. So let's impose odd symmetry first. It's a tiny bit simpler. So we're going to look at a general Lucas sequence with general P and Q, and we're going to say we assume that there's an odd, some sort of solution to that, or the recurrence, some sequence A sub n satisfying this rule that has odd symmetry. Now, A sub 0 then is going to be 0, because A sub 0 is supposed to be minus of A minus 0, so it's got to be, the negative itself has got to be 0. Okay, standard thing about odd functions, they have to vanish at the origin. So, here's the recursion rule in general. So here's what a sub 1 is going to be. It's going to be 0 minus qa minus 1. Okay, but wait a minute. We're supposed to have, it's supposed to be odd, so a1 is supposed to be minus a minus 1. Okay, so if this is both minus qa minus 1 and minus a minus 1, q has to be 1. So that's very easy. Tells you that there's a necessary condition that q had better be equal to 1. In a little bit, we'll talk about that it is sufficient, that if q equals 1, you really actually will be able to have an odd function. All we checked is that it works for 0, 1, and minus 1, which isn't quite sufficient yet. Okay, now what if you impose even symmetry? It's a little bit more complicated. Okay, let's just work out the first three, the 0, 1, and 2 cases of the recursion. So A2 is PA1 minus QA0. Oh, one thing about this style, where I'm not writing things out by hand and I'm working off a pre-prepared thing, I know I tend to go a little faster, but that's where the pause button is really useful. So I said it before. If I am going a little fast and you want to think about it for 2 seconds or just work it out for yourself, press pause, please. So, and if it's still too fast, put it in the comments. Let me know, and I'll go back to doing more stuff by hand. So PA1 minus QA0. A1 is PA0 minus QA minus 1. A0 is PA minus 1 minus QA minus 2. Okay, so that gives us some relationships between 0, 1, 2, and minus 1, minus 2. That should be enough to tell us something about what's going on with the symmetry. Okay, and in particular, it's really good to go backwards with this. What is A minus 1 in terms of A0 and A1? Well, I didn't want to divide yet, so I'm just leaving the Q over here. But I just moved things over in this equation, and I can move things over in this equation to tell us about going backwards. How do you get a more negative term from less negative terms? Now we can put in the symmetry. Okay, QA minus 2 is supposed to be the same as QA2, and A minus 1 is supposed to be the same as A1, so we get that QA2 is PA1 minus A0. Okay, that's a different statement about A2 than this recursion up here. And now I'm going to divide by Q. It tells us A2 had better be this as well as this. And equating those, okay, tells us that Q has got to be 1. Because 1 over Q's got to match Q, P over Q's got to match P, so the only solution for that is Q equals 1. So that tells us in both cases to get either even or odd symmetry out of one of these sequences, we've got to have Q equals 1, the special case. So let's go ahead and and show that that really is sufficient as well. So we're going to assume q equals 1 for now, and let's look at what happens. And this is a very beautiful thing. It's about going backwards again. It says that an plus 1 is pan minus an minus 1. Well, let's just solve for an minus 1. When you go backwards, it's the same rule. Take p times the neighboring one, and then subtract the one that's 2 away, either if you're going forward or if you're going backwards. So the recursion rule is symmetrical. That pretty much guarantees that we'll be able to have symmetrical solutions. Very simple, very general thing. If your setting, if your universe, if your rule of nature is symmetrical, there should be symmetrical and anti-symmetrical solutions to that. It's a very general thing. But let's actually show it. So let's see. Let's produce an odd sequence. Okay, we got to start out with a not equals 0, or else we're just gonna be screwed. Any a1s should work. Okay, these are all. We should always be able to scale these things, so there shouldn't be any constraint on a1. And then we just start using either the forward or backwards recursion rule. The backwards recursion rule, a minus 1, put this in and put this in with a not equals 0, you get minus a1. Oh, good. It's a big surprise. A2 is going to be pa1 minus a naught. Well, that happens to be 0, so that's pa1. A minus 2, that's pa minus 1 minus a naught. Well, that still dies. So that's pa minus 1. That's minus pa1, but that's just going to be minus a2. Okay, and it's not too hard to see that that really does work. It just keeps going on forever. Okay, you can prove it by induction if you're really paranoid about it. Okay, for even it's a little bit trickier. Even there's actually a bit of a restriction here. We know that a1 and a minus 1 have to be the same, and of course a1 is pa naught minus a1. Okay, but we also know what is that going to say? Let's see. Just move the a1 over here. So that means that 2a1 is pa naught. Or in other words, a1 is p over 2 times a naught. So that's something that's not obvious when you first think about it. It's like, well, I'm just going to start with whatever, and I'm just going to start with any a naught and any way a1 it's going to work. It's not. You have to have a special relationship between a naught and a1. But if you have this relationship, then it's going to work. a2 pa1 minus a naught by the recursion, so that's just p squared over 2 a naught minus a naught. Okay, now is a minus 2 going to work? That's really the kicker. Is this really, we got ourselves in a contradiction or something? No. Let's use the backwards recursion rule, and this is the magic. The backwards recursion rule is the same as the forwards recursion rule, and the inputs that you're putting in are a naught is the same, well, that's obviously a naught, and a minus 1 is the same as a1 by the symmetry. So you're taking symmetric data and a symmetric rule going forwards or backwards, of course you're going to get the same answer. So hopefully that convinces you that this really is going to work. I didn't want to write it out in any more detail, but it really does work. So this is a big reason why q equals 1 is a really nice thing. We're going to see deeper reasons for it in a minute here, though. Okay, there's kind of a connection to more deep meaning if we look in the matrix setting. So remember, when we thought about it as a matrix recursion, the key quantity was the matrix A, and that's this guy. Okay, and the determinant of that is exactly q, and I mentioned that before. So the determinant is equal to 1 exactly when q equals 1. Well, determinant 1 matrices are really special. The determinant measures, for example, geometrically, if I think of this as a linear transformation, it measures how much it distorts volume, including oriented volume. So it measures the change in oriented volume when I apply this to some sort of box or some sort of object in the plane. And det A equals 1 means the volume and the orientation are preserved. So geometrically, it's an extremely natural condition to set q equals 1. Okay, and we'll see a relationship to the sine and cosine in a little bit, but I think we'll do that in the next video. Okay, but let's look at the symmetry. There's a very pretty way, slightly more advanced way to look at the symmetry. Basically, do matrix version of exactly the arguments I just did. So A inverse, not hard to take the inverse of this matrix, 1 over q, of course that's the determinant. These guys switch places, these guys switch signs, okay? So that is going that's what happens if I invert the process. If I look at how Vn is created from Vn plus 1. Okay. But what if I just try to naively reverse the order of the sequence? And so this is asking, when is the recursion rule symmetrical, again, in the matrix language? When is inverting the matrix the same thing as just switching the order of the terms? So what we're going to do is we're going to take V sub n, and instead of writing it with the new one on the top and the old one on the bottom, we'll reverse those guys. Well, reversing top and bottom is just this matrix, 0, 1, 1, 0. So what we're going to do is we're really looking at a new version of A, the reversed version of A. What we do is we take, like if you imagine having a vector here, if you imagine having the A sub n and A sub n minus 1 here, we're first going to translate it into our new time reversed version by switching the rows and columns. We're going to apply the old A, and then we're going to, so we're pretending to march forward. We're not trying to invert A. We're just pretending to march forward, but just switching all the indices. And then we still, this is going to produce, this is going to have it switched when it comes into A, and then we need to switch it back. Okay, very common thing that when you do something to all vectors, the equivalent thing to do to a matrix is do that transformation on the left and on the right. This really should be an inverse, but this matrix is its own inverse. So it's really just that. Okay. So the upshot of it is very, very, very simple. If you're always switching the entries of all your vectors, you're just going to take your old matrix. You don't have to think of it as in this fancy way with matrix multiplication. You just put everything, you just switch the row and column of everything. Okay, so 0, 1, 1 goes to 2, 2, 1, 2 goes to 2, 1, etc. Okay, so that's our matrix, the reversed matrix. So that's the naive version of time reversal. Is that the same thing as actually taking the rule and undoing it, going backwards on the rule? Alrighty. So these matrices have better be equal if it's going to be a symmetrical rule, and indeed that says that P has got to equal P over Q, just like we saw before. So Q's got to equal 1, and also minus Q's got to be minus 1 over Q, which that says Q squared has to be 1. But certainly the real kicker is that P over Q, which is coming in here, and P have to be the same. Okay. So some nice observations about, I think it's kind of cool about how these rules work. These questions you'd never ask yourself if you didn't extend into the negative values, and lots of people never think about the negative values, like f sub n for n negative, or Lucas for n negative. But when you do, it tells you that there's something very special about q equals 1, and then from the matrix point of view, it's really about that a equals 1. And we'll talk a little bit more about the deep meaning of that in the next video.